this is going to be a rather related topic where we're going to focus a little bit more on vision, on perception, the limitations of vision and perception. And in a sense, it ties very nicely with one of the questions about reinforcement learning and couldn't agents learn language by interacting with their environment. That's actually what we are largely going to talk about here. Part of the reason to want to do this and to focus on agents learning the environment is actually from the intuition that engaging with your environment is helpful, which I think we all have, is that we kind of, when we talk about sentences, and even when we talk about processing audio, I think we're selling communication short. Much of communication is not verbal. Here you can see two agents, two children, both primates, that are playing a game with one another. There is clearly communication happening between the two, but it is hard to render this communication in a single sentence or to try to segment the video into sort of different phases of the game that are very clearly defined. Clearly, these two children understand each other's body language and they know what game they want to play. There is also a hypothesis that language itself evolved from this kind of communication. That essentially what happened was 2 million years ago or so, we had early hominids that were able to communicate to one another through signs, maybe even through a full sign language, the way that we understand it today. And sign languages are as rich and intricate and full and complete as spoken languages. Maybe they had access to something like a sign language that they developed. And then spoken language was merely a way to externalize this already existing method of communication and make it work over, say, long distances. There are some basic advantages to spoken language over sign language, like if you're in the middle of the Sahara running around, like your hands can be free in order to defend yourself from something, or you can vocalize at very large distances or through the bush where no one can see someone else's hands. So that is another good reason to believe that maybe something like an oral type of approach that tightly integrates vision and language together is actually a good idea for trying to acquire the meaning of something like English. And even more than that, maybe trying to get a little bit closer to the heart of what language and communication actually is, as opposed to simply looking at strings or that are valid inside spoken language. It's also interesting that we understand much, much more about the linguistics of spoken languages as opposed to the linguistics of sign languages. Sign languages have a lot of the same kinds of features of spoken languages, but they're expressed in totally different ways. And then they have many other features that are very unique to them. And for the most part, we don't quite understand how they work. And if you watch an interpreter in sign language, they can sign in very interesting ways and emote while signing in interesting ways to carry meaning that might otherwise be rather difficult to communicate just in spoken language. And so if we believe that the ability to act in the world is related to language, what we wanted to do is start by building a model that connects its ability to act in the world with its understanding of language. So here you have sort of the simplest robotic problem in the world. You have a robot at the red square that wants to go to the green square. And one way to connect these two locations is with something called sampling-based planning. In robotics, you might think that going directly from the start to the end would be a good strategy, but it turns out that that is a terrible strategy. Because as you can see in this case, between the red location and the green location, there's a wall, and your robot can't penetrate it. But it gets much, much worse than this. We don't notice this as humans, but you only notice it when you actually try to get a robot to navigate a room or get a robot to interact with an object. But these kinds of like highly non-linear obstacles where you have to do something totally different, something completely against your cost function, which is get as close to the green square as possible, are not the rare case in robotics. They are actually the overwhelmingly common case in robotics. And so because of that, people, and there's actually a mathematical proof for this, have come up with the notion that you should instead try to sample different trajectories in your environment and hope that one of those samples will eventually intersect with your end position, given that you're sampling from the origin. And if you don't understand the structure of your environment and you don't have a lot of knowledge about different maps and what you should do in different locations, it turns out this is the provably optimal strategy for just getting from the red square to the green square. Just try to explore your environment until you connect the two. And so there's an algorithm. There are several such algorithms, but one in particular is called RT. That is one of the state-of-the-art sampling-based planners. And the way that it works is you pick a direction to move in and you move in that direction. And you just keep repeating this over and over and over and over again. It seems like a pretty dumb thing to do, admittedly, but it is actually a provably optimal thing to do if you don't understand your map. And so every time that you're a robot at the red location, you imagine yourself taking a step in some random direction, and then it's sort of like the world line for you splits into different hypothesized futures. What if I had gone in this direction as opposed to this other direction? And every time that you imagine a potential direction to move in, you find the closest point on your tree that you can attach to it, and you just extend your tree in that direction. It turns out that even though the sampling-based algorithm looks weird, it corresponds to exploring the largest unexplored Voronoi cells in your environment. Essentially, the algorithm is as if it was looking at its whole map, computing which regions are unexplored, and preferring to explore large unexplored regions rather than small explored regions. This algorithm works, and actually many robots, if you've ever used a robot, almost certainly are using a variant of a sampling-based planner like this in order to plan their motion around rooms and in order to plan the trajectories for their end effectors. But these algorithms are stupid. They really assume that you have no knowledge about a map, and that's just not the real world. You have plenty of experience traversing the average American living room or the average living room wherever you happen to live. Maybe if you go into a totally different part of the world, you would sort of take a step back and try to figure out how you should navigate something. But for the most part, you are in well-established familiar territory. And so what we wanted to do is have a deep network, an LSTM, that learns how the robot should behave, and that can control the robot when we are in these environments where we're fairly certain about what we should do. So this seems like it's very, very far divorced from language. But if you look at it from a different perspective, we have an agent that takes action in the real world, but much like those two agents at the beginning, the child, when they were playing a game. And this agent is now being controlled by an LSTM, and LSTMs are good models for parsing languages. And so now we have a model, and you'll see in a second how it works, that connects behavior with something that's somehow connected to language. And then we're going to keep building on that. So this was published in 2018 by our lab in IROS, which is IROS and ICRAR, the two main robotics conferences. What this model does is it treats LSTMs as if they were sort of grafted onto the search tree of this robot. So every time the robot imagines searching a new location, trying to connect its origin to its destination, it also extends an LSTM along that search tree. And whenever the search tree branches, this LSTM also branches. Tree LSTMs are not something that is unheard of, but they are a little bit unusual. And so you end up with a tree-like structure both in your deep network up at the top and your sampling-based planner at the bottom. Now, what this allows us to do is when we want to propose a new direction for the robot to move in, for example, the robot is at the entrance or at the exit to this room that it's kind of trapped in at the beginning. The sampling-based planner may sample a direction that's not conducive to leaving. Indeed, there are very few directions that will actually get you down this narrow channel. It's called a narrow channel problem sampling-based planning. And the narrower this channel is, the fewer random directions are actually going to help you traverse through the channel. And similarly, the longer that it is, the fewer random orientations are going to help you traverse the channel. And so what would be nice is if this deep network that's observing the behavior of the robot and has seen the robot navigate environments like this before could look at the surroundings of the robot and say, well, I know your sampling-based algorithm tells you to go in this direction, but believe me, I'm pretty confident that that's a terrible decision, that when we're at the beginning of a channel, it's better for us to try to just make it through the channel rather than get stuck at the entrance. And so, indeed, what our network does is it looks at the proposal from the sampling-based planner, and it proposes its own direction to go in with its own confidence. And then our model chooses between the sampling-based planner and the deep network, each making competing proposals at every time step. And the deep network actually automatically at training time calibrates its confidence to communicate to our model. So essentially what we have is a sampling-based planner, which is a graphical model, tied with an LSTM that evolve at the same time. And on top of that, we have another very small graphical model that samples from both, conditioned on how confident each of the two models is. And at the end of the day, what this lets you do is integrate observations about your environment into your sampling-based planner and have a much, much more efficient planner. Again, it seems as if we're rather divorced from language, but already we have this LSTM connected to some behavior. We named this planner DRT, or Deep RT. And if you have an environment like this bug trap, that's what this is called. It's a classical kind of environment for testing your sampling-based planners. And you want to go from one location to another. If you search with RT, you can try to figure out where the algorithm is spending a lot of its time searching in order to get to the destination. You see that a normal sampling-based planner essentially uniformly searches its environment. That's not particularly efficient. Whereas when you layer it with the deep network, you see that there are some regions that it hardly explores, and it searches in these long arcs. And the reason for the arcs is the algorithm has learned that the robot has a certain field of view. It can see objects up to a certain distance. And once it traverses the environment in a certain arc, it should never have to imagine traversing the environment that it's already seen and is confident that the object cannot possibly be there anymore. So you get behavior that is a lot more rational. And it turns out that this algorithm actually provides you with an exponential speed up over a regular sampling-based planner. Again, you can see our paper for that. I won't go into this, but it's quite remarkable that all you have to do is connect the deep network with an RT-based planner. You get a better robot, even though that was actually not our sort of original stated goal. Now the question is, how do we add language to this? And this is from a paper that just appeared in ICRA this year. Well, in the previous talk, I had mentioned that when we want to create models that detect actions in videos, what we do is we parse sentences, we look at the structure of those parses, and we create models whose structure reflects the structure of that parse. so that you have different components of the graphical model in the deep network that correspond to different pieces of the parse. That's exactly what we did here. What we said is instead of having one LSTM, how about we have lots of LSTMs? Those LSTMs all get to talk to one another according to the structure of some sentence, and now they get to guide the robot to perform a specific action that we specify in natural language rather than carrying out whatever random actions might connect the start and end location, which is what the sampling-based planner is doing. In essence, when you only have a sampling-based planner or you have only a single network, what you're saying to your robot is find a short path to get to some location I've specified on your map. But when you get to have lots of networks that encode the meaning of a sentence, you can say to your network, go to the car quickly. And some of those LSTMs are going to recognize how should a robot behave when it's supposed to behave quickly? Or how should a robot behave when it's supposed to get to a car? What does it look like when a robot is close to a car? And so what those LSTMs do is they recognize good behavior and bad behavior from the robot, and they push the robot in the right direction. Essentially, there are different LSTMs for each of the different concepts, exactly the same way that there were different LSTMs for different pieces of the parse when we wanted to recognize whether a sentence is true of a video or not. The other big advantage of this is, well, if you have different concepts and you have a lexicon of these different concepts, you can put them together in ways that you've never seen at training time and get your robot to perform actions that don't appear in the training set. And you'll see in a moment that this actually works extremely well. Finally, the other thing that we can do, and this is something we didn't expect, it just so happened, is that we still have the sampling-based planner. We still have this general ability for agents to do things in the world. So when our LSTMs fail to recognize an environment or fail to know what to do next, the robot just naturally falls back and basically brute forces its way to the next step of the problem by using its sampling-based planner. And I'll show you an example of that in a moment as well. So if you have a sentence like, put the black triangle below the orange ball, what we do is we parse the sentence. We create an LSTM for every word in the sentence or every phrase in the sentence. We connect those LSTMs up according to the semantic parse of the sentence. So the LSTM for orange would be connected to the one for ball, black would be connected to triangle, a black triangle would be connected to below, below would be connected to orange ball, and all of these would be connected to pick up and turn, where at the end you're making a single decision for what the robot should do based on how all of these LSTMs are reasoning about the problem together. There are some very nice advantages to doing this, like you can examine the intermediate representations of your various LSTMs. For example, we can stop inside this tree of LSTMs that represents, say, the sentence approach the red car above the cup, and try to decode the internal representation of the above LSTM and see what it thinks above means relative to the environment of the robot, as opposed to what the word cup might mean relative to the environment of the robot, or what the cup above might mean, or even what approach thinks the next action might potentially be. What we did even more recently is we came up with a model that doesn't just take as input first order logic, but remember at the end of the previous talk I talked about LTL, it can take as input statements in linear temporal logic. In other words, you give me a statement first order logic or LTL, I parse it, and I build this network structure where each one of these words or predicates is an LSTM. Each one of them has its own state. Each one of them communicates to the LSTMs below and above it. And together, you can show that mathematically, this structure can correctly capture the meaning of a formula in LTL. So when you give me a new formula I've never seen before, all I have to do is go to my lexicon of RNNs, arrange my RNNs into the structure that corresponds to your formula, and all of a sudden I get a robot that behaves according to this formula. And now we're kind of moving a little bit closer to language, right? I mean, that's one of the things that you want robots to do. If you believe that a robot understands what a sentence means, you would like to be able to give it a new sentence and have it actually follow that sentence. So that's what we demonstrate doing at IROS this year. What's even more exciting is that we can demonstrate that when you understand language in this way, you can actually generalize in ways that previous work cannot. There was a paper about 2 months ago or so on models that attempt to generalize to new grounded environments. It was by Andrei, Jacob, and folks. And what they showed is that if you have a robot and you show it examples of, say, manipulating a red apple, but then you don't show examples of manipulating a green apple, but you use that concept in a sentence, many models are unable to generalize from one to another because they don't understand that there's a separate concept of apple and a separate concept of green and red, and that they can be combined together. They have this general understanding of what the sentence means, but that meaning can't be broken down into parts, which is exactly what our model does at training time automatically. At training time, when we train these models, we don't show them what the different words mean. All we show them is the behavior that a robot that understood what this sentence or what this formula means in a particular environment would do with that knowledge. And our models automatically learn to basically break that knowledge up into pieces and acquire the meaning of the word factory independent of the meaning of the word gem, independent of the meaning of the operator and. So essentially, these models are capturing the compositionality that we see in language, your ability to combine together words in novel ways, but they're doing it in a very, very direct way by composing subnetworks into bigger networks. So the paper that I mentioned by Jacobs and folks released a data set called Gscan, which is all about grounded robots perceiving their environment, following linguistic commands in that environment, and attempting to generalize. If you fully supervise robots, so you show them every possible scenario and every possible linguistic input or every type of linguistic input, both the previous work and our work do exceedingly well. Essentially, they do, they're up to the error ceiling for this data set. But all of a sudden, if you leave out some concepts, for example, you don't show the concept of a red square to previous models, the performance gets much worse. They only correctly execute sentences with red squares 24% of the time, whereas our models, because they're compositional, can execute sentences like this with about 90% accuracy. Same deal. If you leave out concepts that have to do with spatial relations, previous models do terribly. These kinds of compositional models do very well. And what's even more exciting is as you give the robots harder problems, you give them problems that take longer and longer steps to execute, previous models fall apart almost immediately. They can only solve problems that are as difficult as the problems that they've seen in their training set, whereas compositional models like these can continue to solve much, much more difficult problems. We've done this out to length 30 sequences, and our models very, very gently degrade in performance. I had mentioned that one of the things that models like this have going for them is they still have that sampling-based planner inside of them. They're not just guided by the deep network. Now, part of the reason they're not guided by the deep network is deep networks, when they're untrained, they have very suboptimal behavior. An untrained reinforcement learning agent is not rationally attempting to explore its environment. An untrained RL agent is just following a crappy plan that was randomly initialized. On the other hand, if we have a model like this, an untrained LSTM is very not confident, has very low confidence in what step the robot should take next. It's going to produce a fairly uniform distribution over what the robot believes about the environment and which direction the robot should move in. And so that naturally allows the robot to use the sampling-based planner instead, because it notices the deep network is not confident. So here's an example of that. The robot is sort of the two L shapes. It's a paddle-based robot. This robot was asked to put the block in the cup in the simulated environment, and it does so. But what's interesting about it is we've never actually showed this robot any examples of a cup that has a lid on it. Normally, if we just ran the deep learning-based LSTM, even the compositional LSTM, on top of this robot without having the sampling-based planner, it would be completely confused. It has no idea what to do. This data looks entirely unlike anything in the training set, and so it does not actually manage to successfully put the block in the cup. But with the sampling-based planner underneath, the LSTM is confused. The sampling-based planner eventually finds a way to do something with the cup where the LSTM now knows what it should do next, and that results in the rational behavior that you observe. There are some reasons to believe that this kind of compositionality in exploring your environment and in taking rational actions in your environment should exist somewhere in our brains. There's great evidence from Matt Wilson, who usually talks at the summer school and will do so this year, for rodents that navigate mazes and how those rodents think about different parts of mazes. They're able to put together different pieces of mazes that they haven't seen before. So somehow, this kind of compositionality that we build into these networks explicitly also exists inside the brain. Now, one of the things that would be nice to do with these models is have them execute lots and lots of different tasks for us, rather than having to build a single model that is very, very good at navigating environments, and another model that's very good at, say, captioning videos, and another model that's good at searching videos, and another one that can acquire language from perception. Right now, multitask natural language processing is absolutely a thing. What you do is you train your transformer to perform lots and lots of different tasks, and then you decode its representations and process them at test time to, for example, classify sentences or figure out what the relationship between sentences is, etc. In vision, we do kind of similar things. We train encoders that have multiple decoders for lots of different tasks. For example, we might take as input an image and attempt to decode how many objects there are in this image, attempt to decode the different types of objects that are present, or the 3D depth of the environment if we're given as input a 2D image. Then you get a multitask loss. And our hypothesis is, well, humans have a fairly rich understanding of our visual environment. And so maybe asking models to do more than a single task at a time will allow them to build sort of similarly rich understanding of the environments, and you'll get a more reliable model overall. What we've been working on is a different way to do multitask learning. So instead of having to train a model to perform lots of different tasks, what we do is we train a model to perform one task, but then we actually use it in different ways by wrapping it in a very, very small amount of code. We've already seen this in action so far. I just have to point out what the relationships between these different models are. So very often when you think of sort of big problems in machine learning and the kinds of problems that people tackle in different communities, a few kind of quintessential problems often crop up, like recognizing what's in an image, retrieving videos or images from a large corpus of them, generating captions for images, or visual question answering, or disambiguating what a sentence might mean, or learning parser, a syntactic or semantic parser, or deciding whether two sentences mean the same thing or not, or translating between two languages, or doing common sense reasoning, planning in new environments, or following commands. And we could keep going like this. There are a few big problems that each field has, and every field addresses these problems with different models. With different training sets, different test sets, different loss functions. But it sure would be nice if we had a single model that could do all of these. Not only that, we know that you don't have to train children independently to perform every one of these tasks, even though we've kind of artificially split them apart into different fields. Children can learn, some knowledge by observing how people answer questions and then use it in order to do common sense reasoning, or use it in order to plan or follow commands, or disambiguate what some sentence that someone told them means. All of this is based around that original predicate that I told you in the previous talk, which is we learn a joint distribution between sentences and videos. And every time we build one of these models, so the heart of the model is always this joint distribution. You watch videos, you see what people have to say about them, and you learn which sentences go with which videos. And we learn a generative model so that we can feed in either a sentence video pair and produce a score. Is this sentence true of this video? Or we can feed in a sentence and sample videos, which allows us to imagine hypothetical scenarios that might be true of the sentence. Or we feed in videos and we imagine hypothetical sentences that might go with this video. So that's what sort of the basic recognition capability is. That's the only training that's really required for the model. Then we can do a bunch of tricks on top of this and just sort of manipulate this model in different ways. For example, if you want to retrieve videos, that's very, very simple. You just score every video against your sentence, and you pick the videos that have highest score. Or if you want to generate sentences, you just score every sentence against your video and pick the highest scoring sentences. Of course, it's a little bit more complicated because the space of sentences is infinitely large. But it turns out that there are some very efficient search algorithms that will let you prune away the space of sentences quite quickly and narrow down onto which English sentences are potentially true of the video. And we can keep going like this. We can keep manipulating this predicate over and over again. And really what we did in the last talk is we wrapped this predicate, this ability to connect sentences and videos, or the interpretation of sentences and videos. We wrapped it in an algorithm that could take a gradient through it so that we could learn the parameters of these sentences to get a syntactic and semantic parser. It's kind of interesting that we can perform lots of different tasks as long as we choose the right primitives, just by reusing those primitives without really having to learn anything that's task specific. What I'll show you next is an even more interesting way of using these primitives to do paraphrasing and translation that allows us to do something which is figure out if two sentences are paraphrases of one another without actually ever seeing an example of a paraphrase, and translate between two languages without seeing an example, a line between those two languages. But everything that we did in robotics falls under this general framework as well. For example, whenever a robot wants to plan what it should do in the future, what it's really doing is it took as input a sentence, it built this collection of LSTMs that allows it to recognize its behavior. That's just a video recognizer. It's a synthetic video that the robot is producing for itself, but nonetheless is a video. And then it's asking itself, what completions for this video would result in the sentence being true of my behavior? That's exactly the same thing as asking, how do I make a good plan that follows the command that the person gave me? So I think this will become clear when we talk about paraphrasing with vision, exactly how we can manipulate this single predicate over and over and over again in order to perform lots of tasks. So paraphrasing is the problem of, I give you one sentence and another sentence, and I want to know the relationship between the two. This is also related to a problem called natural language inference, which is quite popular in NLP these days. There, the issue is I give you a sentence, another sentence, and I want to know, does the first sentence imply that the second one is true? Does the first sentence contradict the second one, or are they just unrelated to one another? If you only had this predicate, the ability to score a sentence in a video, then you could actually solve paraphrasing problems with it. You could take this predicate, compare it against every video on YouTube, and then you would get a distribution over those videos, a video sentence data set, where, I should say a video likelihood data set, where every video has a score associated with it. You could do the same with your other sentence, and the idea is if two sentences mean precisely the same thing, they will have the same scores no matter what visual environment you apply them to. That's kind of the part of the definition of meaning the same thing. If the first sentence implies the second one, every single video where the first sentence is true, the second one will also have high likelihood in. And if there's a contradiction, again, you're going to see that in the pattern of likelihoods. So all you have to do is measure something about the pattern of likelihoods of these two sentences over a large number of videos, and you can tell the relationship between them. The problem with this is it basically doesn't work because you can't possibly score every video on YouTube. But even more than that, as the length of a sentence goes up, the likelihood that a video actually exists for that sentence becomes exponentially smaller. Almost certainly there's no sentence that or no video that corresponds to the sentence, "The man waved the banana on the airplane wing" on YouTube right now. So instead, we can use the fact that this primitive is generative. So we take a sentence, we sample lots of videos for that sentence. Now we have a video score data set. We score the other sentence against those same videos, and we compare those likelihoods. So it's kind of like paraphrasing with imagination. We're paraphrasing by imagining scenarios without ever having to have really seen them before. It turns out the sampling process, you can actually visualize the sentences that are sampled. So for something like Alice carried the chair away from the backpack, we can decode the representation of the model and see that the sentences, once we put some clip art, the animations will put some clip art on them, do actually look like someone carrying a chair away from a backpack. And it turns out against state-of-the-art models, this model actually does quite well, because normal models that have never seen anything about the environment that they're in get confused about which words imply which other words and about the basic physics of the environment. For example, they don't understand that carrying something implies that you hold it. That's just like a basic fact that as humans we don't usually say to one another because it's so completely trivial and implied by the physics of the world. But our model actually does that. And the same kind of thing happens when, for example, there's some symmetry in how an action is carried out, or when an action takes away an object from someone. And we have a paper on arXiv about this. You're welcome to have a look. The thing that we've done most recently, though, is use this model to translate between languages. So what you can do is take a sentence in, say, Chinese, imagine lots of videos for this Chinese sentence, then sample those videos from this sentence, so you get a video score data set again. Have another model that's trained in English, it's never seen a single Chinese sentence, and just ask what sentence best describes this video on average. And then you get to translate one sentence from one language to a sentence in another language without ever having seen the same sentence in the two languages, so you have no parallel corpus. This is kind of like humans acquire language. You can live in one country and talk to the humans in that one country in one language, move to another country, never speak in the previous language, but you can still actually learn that second language and communicate and then eventually translate between the two. So we think this is both a model that works and works with very, very little data. It does zero-shot generalization, and also a model that is more cognitively plausible to explain how people are performing these tasks. And it's elegant that all it's doing is manipulating a single primitive in order to perform all of these different tricks. I think that we have to move to the poster session, so I think I will skip this piece. You can come to our poster session, and last time David talked about ObjectNet and issues that have to do with vision and the problems that you have when you create vision data sets. I just want to say one thing at the end, which is to talk briefly about the various things we can do at the intersection of language and vision.
So Andrei,
yeah.
Sorry to interrupt. Just to let you know, you have until 3:30. So there was
until 3:30. Okay.
Yeah, and I mean, of course, you can have time for questions. I just wanted to let you know that you still have a little bit of time.
Thank you. I think I'll leave that time for questions then. And maybe I'll talk a few more extra minutes about the various things we can do.
Sorry to interrupt. I just wanted to
clarify. No, thank you. That's very helpful. So here are some things that we can't do at the intersection of language and vision. And for the most part, we're so far away from being able to do that we really have no clue about how to approach these problems. For example, how do you visualize an entire story, like say an entire book? Or how do you watch a movie and then write a summary of that movie that's at the not at the level of what the people did, but at the level of what was the overall story arc? We can understand sentences at the level of a 2-second movie, but figuring out what even a children's book means and what the overall story development and trajectory is, and what the intent of the various agents in that book is, really, we have no idea how to do. We really don't know too much about 3D vision. We have pretty good 2D object detectors these days. The 3D object detectors are considerably more unreliable. We also don't quite know how humans build the sort of rich 3D representations that we feel that we have the world that surrounds us. There are also some serious issues to do with physics, where you need to understand forces and contact relationships. For example, if you want to figure out that I need help, well, if I'm standing in front of a door and I'm holding some objects and they appear to be very heavy, probably I need help from you. If, on the other hand, I'm holding something very light that I could just move from one hand to another and reach for my keys and open the door, probably I don't need help from you. This knowledge of physics really plays an important role in understanding the intent of other agents. But even when you look at something as simple as what action is being performed, physics still plays an important role. For example, here's a helicopter holding a telescope. You may never have seen a helicopter hold an object like this before, but clearly the word hold applies, and we can have conversations about the action that's taking place. No model today can generalize from a person holding something to a helicopter holding something. Even more than that, it appears that our entire sort of method of understanding physics computationally leaves something to be desired. These animals use objects in ways that are very intricate by comparison to what we're able to simulate. But just the fact that our friend here can build himself a hammock is quite amazing. If you think about the immense computational resources that we would have to devote to do some sort of cloth-based simulation with the robot and have it try to imagine different orientations of this cloth and different actions that it could take in order to build a stable hammock, we have no idea. There's literally no robot in the universe that you can give two ropes like this and a hammock to and say, make a hammock and get in. And that isn't even something that's human, which is something like coherent stories. That's a very basic ability we don't quite understand. Segmentation is also still a huge problem. Even though we do object detection these days on data sets that have even tens of thousands of object classes, segmentation data sets are very small and they're not particularly intricate right now. We don't quite understand how to do segmentation at scale reliably. And if you want to understand, say, different parts of different objects, for example, you want to understand the configuration of that tarp because you need to manipulate it, you have to understand it in 3D and you have to be able to segment it. It's not enough to say that you have a bounding box around that tarp. You have to know its precise 3D geometry and its edges. And of course, we don't understand very much about parts and low-level features either. And even the concept of a feature is something that is a little bit unclear right now. For example, here's a feature detection task or a classification task that you've probably not had to do very often in your life. One of these animals is animate, and the other ones are stuffed animals. And you can probably guess with high reliability which one of them is animate. I don't think anyone as a child ever showed you pairs of puppies and stuffies and had you train a classifier in order to perform this task. But nonetheless, you can, and we don't quite know how to do zero-shot generalization to settings like this. That's before we get into issues of things like theory of mind. If you think about the kind of behavior you saw in the video at the beginning of the video, which is that communication between two agents that was nonverbal, well, that requires not just the ability to parse that communication, which is where we're going with our models, but the ability to represent what another agent is thinking. That's why, for example, when you look at an image like this, you probably have a visceral negative reaction that that baby should not be allowed anywhere next to the stove. But if I just replace that baby with an adult, that's just a normal picture of a kitchen that you couldn't care less about. You understand something about the theory of mind of young children and the fact that they probably will hurt themselves. And not only can you understand the theory of mind of individual agents, but you can understand the theory of mind of multiple agents at scale and what the relationship between them is and how you should behave relative to them. You don't behave the same way at work as you do at home, and you don't behave the same way to someone that you don't like relative to someone that you like very much. And we know that animals do this. For example, here are two monkeys where you should know that monkeys, very much like both cucumbers and grapes, they will work all day for either of them. And this is a simple task where a monkey is given a rock, it returns it, and it gets a cucumber or a grape. But the trick is that grapes are much, much, much better than cucumbers. And you can see the first monkey saw the second one get a better reward for the same action that it performed. I mean, think about the kind of inference that's required to understand, sort of equal pay for equal work. The first monkey is realizing, and you'll see a second, it takes the rock and it'll bang it against its enclosure to check, is this a legit rock? It sees that it's getting a lesser reward for the same amount of work. It has to understand the concept of work, of reward, of relative reward. We have no idea how to even computationally represent this kind of concept, how to encode it in the first place, never mind how to acquire it, never mind what kind of data set might be required in order to do so. But even more pedestrian things turn out to be sort of full of landmines. For example, modification. You might think that the word small and large, of all the things that we can learn in computer vision, telling me that something is small or something is large should be pretty straightforward. You just measure its relative size and we're good to go. But it turns out that that's not true at all. And you know that it's not true. It's just so incredibly intuitive that that's false to you that you never think about it. Roadrunner used to be one of my favorite cartoons as a child, and it's one of the prime examples of this. You knew exactly what was going to happen. Our favorite friend managed to make it through the tunnel, and now our coyote tries the same and fails. And this is pretty funny, but there's actually a deep reason why it's funny. And that's because the same object can be both open and closed at the same time. Normally it doesn't manifest in this humorous way, but a cage can be closed for an elephant and open for a mouse. Or my backpack is closed to books, but is open to air, and unfortunately also open to water. you have an intuitive understanding of this. It's just we normally don't think about it. We take it for granted. The same thing happens for large and small. A large city is very different from a large laptop, which is very different from a large mouse. Understanding the scales and understanding when a scale is relative to what is actually extremely difficult and is an open area of research. And that's before we get into even more complicated things like metaphors that I alluded to in the previous talk, where you have to understand the concept that the stock market is going up. That is a concept that is so difficult that we can't even begin to get any purchase on it right now. Or Gabriel's favorite example of computational humor and why is something humorous. Again, there's some work on that, but essentially we're at step 0. We're not even at step 1. So with that, I just want to thank the many wonderful people that contributed to this work, both at MIT and elsewhere. And I'm happy to take any questions that you might have.
Great. Thanks, Andrei. The first one is from Colm Wyeth. What do you mean by knowing nothing about your map? Most robots have some kind of sensor and often construct a map. It doesn't seem like this sampling would be optimal for a LiDAR-based robot, for instance. So under what circumstances is it probably optimal?
So there is a difference between knowing the structure of your map and knowing how to traverse your map. So imagine for a second that I give you, one of those like kids mazes where you have a piece of paper, you have a maze, and you start at some location and you need to make it out of the maze. You see the map there, but you don't actually have knowledge about the environment because you don't understand the cues in the environment that would allow you to solve the map. Now, if you have already done this maze, probably you recognize, I see this little U-shaped thing next to this L, and I know that I have to turn left over here. So that's what I mean by the distinction between having the map and understanding your environment. Having the map is just perceiving what's going on. Understanding your environment is understanding the structures and cues in the environment that allow you to plan efficiently.
Thanks. The next one is from Khwaja Wisal. What do you mean by compositionality? Is it referring to the structure of deep networks relating to sampling-based planners? Can they find if there is no solution to the given problem, or they always produce a solution?
So what I mean by compositionality is this is a concept from linguistics that also exists in mathematics. In linguistics, you would say that multiple words combine together in some rational way in order to sort of have the meaning of a sentence, and that you can undo the process by parsing the sentence and sort of recover how those words were composed together. That sentences are not bags of words, they're not sets, they actually have internal structure. Mathematically, what we really mean is that you have a collection of functions and they're applied to one another, and they're applied in some structure, some say tree-based structure to one another until you get your final result. In this case, what I mean by compositionality is it's more in the mathematical sense that we have multiple deep networks that they behave as functions, and one takes the input from another one, that we arrange them hierarchically, except that we derive that hierarchy for the mathematical composition of those deep networks from the compositional structure of language. So whenever we know that the word red modifies the word ball, we're going to take the model for red and the model for ball and combine them together by passing the output from one as the input to the other one. That's sort of what I mean by like reflecting the compositional structure of language in the compositional structure of a deep network. I think the other part of the question was, does the model always produce an answer? No. It turns out what the model does is it estimates both the direction that a robot should move in and whether the robot has completed its action or not. And if you ask it to do something that is impossible, or something that's nonsensical in some strange way, or an object, for example, is missing from the environment, so it can't possibly manipulate it, the network will never say that it's done. The robot will just keep doing things forever.
Thanks. And the next one is from Nimrod Shaham. In both the robot navigation task and the command understanding one, you were adding more and more LSTMs. Would you expand a bit on how the training is done and how computationally expensive the continuous addition of LSTMs is? How big do those collections of LSTMs become, and does it limit the task complexity those models can perform?
That's a great question. The answer is both yes and no to limiting the complexity. So as you add more LSTMs, your model becomes linearly slower. Every LSTM that you add adds a small constant amount of computation to your model. Now, in a sense, that's good, because if the answer was we were slowing down quadratically or exponentially, adding additional models would be a real problem. The number of LSTMs is proportional to the parse of the sentence. First order approximation, let's just call it the number of LSTMs is proportional to the number of words in the sentence, because long sentences tend to have a lot of meaning, short sentences tend to be easily encoded. And so if you have, say, a 10-word sentence, you can fairly easily execute that. Running 10 stacked LSTMs on top of one another is really, really no big deal these days. On the other hand, if you try to, say, follow a 10-page request to your robot, all of a sudden things will break down. That even the linear scaling is insufficient. We need to find some way to scale sublinearly as the query becomes longer. And you might think that, oh, well, I'll always only give short commands to my robot, but there are lots of times in your life when you follow very complicated commands. For example, whenever you're driving, there was a manual that you read at some point that told you what you should and shouldn't do and how to be safe. You have that somewhere inside your mind while you're driving. We have absolutely no idea how to encode that. And as for training, that's a little bit of a longer story, but training is also fairly efficient. It doesn't take all that long to train these models. All you have to do is essentially create the composition of LSTMs. You can think of this as I have lots and lots of stacked LSTM models that happen to share weights between them whenever words are shared between the sentences.
Great. And one last quick one from Khwaja Wisal. I think transformers were meant to do the same thing to understand the compositional structure of language. That is, what is self-attention is by calculating query, key, and values. Do you use that?
We do not use transformers. It's a good question how much of the compositional structure they could capture here. There are papers that have tried to probe the sort of understanding of different kinds of models. For example, there are batteries of tests these days for NLP systems where they systematically try different sentences that have never been seen before and see how the models can parse them. And it appears that when you do that, sentences that are systematically generated, so they don't have the kind of sort of biases that you see in data sets, say, derived from the web, they do appear to trip up even transformer-based models. That transformers are not perfect at generalizing to compositional concepts. That being said, it's true that they do have a piece that should predispose them to that. It's an interesting question to see how the same trick that we're doing with LSTMs could be done with transformers. And perhaps this is related to the previous question that maybe there's some way to change the self-attention mechanism, make it more compositional, and like that prevent the need from having to add additional models and scale linearly as the complexity of the input increases.
Thank you very much, Andrei. Those were two beautiful talks.